Hey, hi everybody. Can you hear me all right? Okay, good. Okay, so I'm going to be talking about an extended abstract. The link for the current draft, which is in flux a little bit, is right here. So it'll be at the end of the talk as well if you want to take a look. Okay, so the inspiration for this work came originally when I was reading this nice article by Jimmy Koppel, where he goes over a number of applications of defunctionalization or continuation passing style conversion and defunctionalization. And one of the applications in particular stood out to me, which is taking a recursive program and through a series of refactoring steps deriving an iterative algorithm. And the reason that one stood out to me is because I had been working for a while on a technique for doing granularity control for kind of multi-core parallel programs, fork-joined parallel programs. And it seemed intuitively like I could take this idea and extend it a little bit to have a new application where you could use that technique, the defunctionalization plus CPS conversion, plus some other stuff to get a multi-core parallelization that has good granularity control and can handle some tricky parallelization problems. So I'm going to use this kind of simple running example to show you how it works. So we're going to think about a binary tree. I'm going to be kind of working in a pseudo C++ language. We're going to be working with a binary tree where each node has like an integer value and there's a pair of child pointers. And we're going to be working on this algorithm which calculates the sum of the values in a given binary tree. Okay. So to get started, let's just do sort of the simplest kind of parallel transform we can do with the tools that are readily available. So first, we'll just take our source program, and because this is just for notational reasons, we're going to allocate space for the results of the two recursive calls. So like we have these two recursive calls here. I'm just allocating an array called S to store the recursive calls. Also, I'm using this. I'm going to use a red star to indicate where we are, and I'm also going to use this kind of funky notation just to say that to compact these recursive calls into like one statement. Okay. So just stop me if anything's not completely clear. Okay, so we can pick. There's a number of implementations we can pick to parallelize this code. I'm just going to kind of introduce a little notation here that kind of captures what they do. It's a binary fork point, which is taking two statements, saying that these two can run in parallel, and starts them running in parallel, and then guarantees that by the time this join point executes, that that all of the writes performed by these two statements are present in memory for this join point to see. Okay, there's a number of implementations, Silk and TBB and so on. We can pick from those. They're pretty good implementations. Oops. But we have a granularity control challenge because if you look at that tree data type, we can have any number of different types of tree data structures. They can kind of range from nice and balanced and large, which are good for parallelism, or they can just be a long chain or something degenerate like that. So this is sort of a classic granularity control problem here, because every time we execute one of those fork join instructions, we're paying a cost. It might be a small cost, but it adds up, and it can very easily overwhelm any advantage of parallelism, even if you have a very highly optimized and engineered system like Silk or TBB or so on. So this is sort of the classic granularity control problem. There's sort of a side problem, which is just that these fork join implementations typically allocate frames on the C stack, and the C stack is limited fixed size. So it doesn't take a very large input, like a degenerate input, to overflow the stack. So this is sort of a tricky parallelization problem. This isn't the aspect of the problem that I'd like to focus on, but it is something that's practical and would stop like a good implementation of anything that wanted to traverse that sort of data structure efficiently. So the refactoring technique I'm going to present deals with both these problems. So at a high level, they're going to take our reference algorithm and push it through two independent refactoring paths, one to obtain a parallel algorithm at the end, and the other one to obtain a serial one. The interesting part comes when we're going to merge the two algorithms and get a version that sort of uses this heartbeat scheduling idea. That's going to be like kind of the conceptual glue we're going to use to do the merging. And basically what it's going to do is going to interleave carefully between the sequential and parallel execution modes of those algorithms so that we get sort of the best of both worlds. So let's see. So we're starting with this reference program. We made a first refactoring step to make it a fork join program that has these problems we mentioned. Now we're going to lower that program to a kind of continuation passing style. So to do that in the parallel world, I'm going to have to sort of change our interface to something a little bit lower level that kind of lives behind the scenes. So we have these three functions. There's one to create a new task given a thunk. The thunk is basically going to be what the computation that the task does when it's scheduled. There's a fork instruction which is going to set up dependency edges and start a task running. And there's a join instruction which is going to tell a task downstream that its dependency edge has been resolved. So those are the three instructions. I'll just step through quickly what it does. So let's suppose we have a current task that's running. We can create a new, we're going to typically create a new join task that's going to handle the results of this sort of fork point. Call that TJ. Now we create a child task. And at this point, you can see that the dependency edges are such that neither of those tasks are ready to run. They both depend on the parent task. The fork instruction basically sets it up so that the child task is ready to run, and it's got a dependency edge that's incoming on the join task. So like once both the parent task and the child task have finished, then the join task will be ready to run. So that's sort of what's going on down here. So let's just suppose that the child task finishes before the parent task. The dependency edge goes away, and then when the parent task finishes, that dependency edge will go away and the join task will be ready to run. So that's the interface we're working with. Okay, so now let's just return to our example. So we have this example written in terms of fork join. Our transform is going to basically take the fork point and give us something like this that's going to basically introduce a new child task for each of the two recursive calls. And it's going to set up the dependencies and start them running using the fork instruction. We're going to take the join point here and lift it out into a new task. Oh yeah, and the CPS aspect of this is that we've introduced the continuation K, and that's where we're going to send the result once we've gotten it from the recursive calls after they've finished. So that's the kind of CPS conversion here. Okay, so we finished that. Now we're going to defunctionalize the continuations we introduced. That's going to basically, we have two continuations in this program. One we've already seen. This is the one that takes the result of the recursive call and stores it, and then resolves the dependency edge on the join task. Okay, that's one continuation. We'll call that KP branch. And then there's like sort of the top level call, which just takes the overall result and writes it out to memory. Okay, we'll call that K term. Okay, so this is just the typical defunctionalization then. So basically for each of these two continuations, we define a data algebraic data type that kind of represents each as a tag and tells us has a record that stores all of the variables that are free in the body of the continuation. Okay? So that's sort of the first step of this defunctionalization step. The second part is we rewrite our algorithm. So basically what changes is that the continuation goes from being a function to a value of the cont data type that we defined. We replace calls to the continuation to calls of an apply function, which we're defining below. And in this case, where we had that lambda expression, we just rip that out and replace it with a corresponding instance of our algebraic data type. And now we basically took that code that we ripped out for this KP branch continuation, and we put it in the apply function where it's being handled. Okay, so that's and yeah, we do something similar for the top level function. Okay. Okay, so now we have refactored our parallel algorithm so that it's going to be ready for merging. So we're done with that part of it. Now we're going to return to our reference program and start with the serial refactoring. So I'm going to kind of run through this part fairly fast because it's already covered in Koppel's talk, and it's pretty much the textbook series of steps one would use. So basically what we do, starting back from our recursive function, we CPS convert. It gives us two continuations, one for the first recursive call and one for the second. It might be a little bit weird, but there's two continuations here, and only one in the parallel version, because here there's a little asymmetry that we're going to end up having to store this value in the second continuation. So anyways, it's just a minor difference. But okay, so we've CPS converted. Now we're going to defunctionalize the continuations. So like before, for each continuation that we introduce a case for our continuation data type. One we'll call KS branch 0 for serial, and KS branch 1. And like before, we give each of these data types the we give it a place in the record for each of the free variables in the body of the continuation. So what we get in the end is this is the defunctionalized version of our serial algorithm. So we just ripped out that first continuation we introduced and put it in the apply function. That would be this one. And then this one we ripped out similarly. It creates a value, sort of like pushing on the stack. It creates a value for the return continuation corresponding to the second recursive call, which is this one. Okay, so that's now we've gotten these two algorithms in somewhat similar shape. They're both CPS converted and defunctionalized. Their continuations are defunctionalized. We have to take a few more steps though with the serial algorithm because it's still pretty slow. It's using recursion. It's not in good shape for a good sequential algorithm. So here all we do, if we go back to the apply function of our sequential algorithm, we just eliminate the recursive call. There was a recursive call in the apply function, just corresponding to like walking back up the stack as you're returning from function calls. We just eliminate the recursion there by doing a tail call elimination of the apply function. So that just gives us this while loop, this outer while loop. Okay. And then we go to our sum function. Actually, there was only one call to apply in the sum function, so we just inlined it. So now we have this big blob of code. It's starting to look more imperative. Finally, we do the Taylor call elimination of the sum function, removing all of the recursion finally. And now we get this structure, which is the original. This is sort of a stack-based implementation of our original recursive algorithm. It's completely sequential at this point, but as you can see, so this outer loop is walking down and to the left on any given input tree, and this loop is walking up or to the right. So that's what's going on here. So you can see this loop, when we see that the node is not null, we just descend to the left branch, and before we do that, we create a return continuation for dealing with this second branch, the right branch. So anyways, not too important how it's implemented. The point is, this algorithm is pretty good for a sequential algorithm at this point. Okay, so now we're ready for the interesting part, where we merge the two algorithms. So before we do that, I have to tell you about heartbeat scheduling. So the basic idea in heartbeat scheduling is we want to amortize the overheads of spawning tasks, basically the cost associated with calling that fork instruction or creating tasks, all that stuff associated with managing tasks. We want to amortize that against useful work. Okay, so for that purpose, we introduce this kind of notion of a heartbeat. So a heartbeat is the event that happens when we've paid the cost, we've done enough useful work that we can now amortize the creation of a task. And we're going to call so we have like the cost of spawning tasks, and we're going to call the time in between heartbeats this amortization parameter h. Okay. And that h can be obtained. That's a machine-specific thing. It's not algorithm-specific. You just obtain it once on a given machine. So let's just see how it works. Let's just suppose this is sort of a sample trace execution, a sample schedule of our program, say, given like a perfectly balanced binary tree. So this is just sort of each of these nodes, vertices corresponds to an instruction, and each edge to a dependency. Okay, so I'm going to just sort of step through what heartbeat scheduling does with this kind of. So this here is what corresponds to the fully parallel schedule, if we just did no granularity control at all. Okay, so in heartbeat scheduling, which is I'm going to show you below. Oh yeah, we're going to use this parameter. Heartbeat rate is going to be 4 in our example. So let's just say with the heartbeat scheduling approach, we're going to start off executing in a serial fashion. But when we get to the first fork point, we're just going to mark it keep in mind that it's an opportunity for parallelism, but we're not necessarily going to parallelize it yet. We're going to keep executing sequentially until we reach the second fork point. We're going to keep executing sequentially because only now have we paid the cost for creating a new parallel task. So the amortization is paid off. And this step that we just call this a promotion, this just means that we're going to spawn a task now. And we have 2 possible tasks we could spawn, but there's one that's better, provably better, and that's the outermost one. It's always the outermost one. This is sort of a typical pattern in sort of scheduling for fork join. So we're going to promote the outermost one. That's a little bit awkward, though, and that we're going to see. That's one of the tricky aspects of this refactoring is that usually, you're working locally in a sort of DFS style, like with a sequential schedule. With heartbeat scheduling, you want to work locally most of the time, but when you do a promotion, you have to go out to the outermost instance of parallelism. Okay. Oh yeah, and then so finally now, after we've done the promotion, we're going to keep going sequentially. And effectively, what we do, because we've continued on, we've sequentialized this inner join point. This inner fork point. So basically, we've because it's small. Like there's no point in parallelizing it. So that's sort of the way that Heartbeat gets its sequential efficiency. Okay, so now let's just map that idea back to our algorithm. The first step is we have to introduce the heartbeat into the program. So this is our sequential program. The step that we take is we have to introduce what a promotion point, so to speak. So every time around, like this is the sort of loop that's descending into the tree. Every time we take a step in that loop, we're going to say if a heartbeat has occurred, we could just implement that with like a counter or something. If we've taken sufficient steps to amortize creating a task, we're going to try to promote. And the promotion is strictly parameterized over our calls, or over our continuation, or current continuation. It's just a rewrite, so to speak, on the current continuation. Okay, and the tricky thing about this step is that we have two loops actually, so we have two of these events. We can't go for some unbounded number of steps without having checked for the presence of a heartbeat. Okay, so the second step is a little trickier. Like as I alluded, we have to kind of do a little surgery on our continuation, on our call stack, in order to implement promotion. So when a promotion happens, well, I'll show you when a promotion happens. So this is sort of a bit like the situation we looked at before, but now we'll map it to our running example. So let's just suppose we start running on this. This is our input tree here. Let's suppose we get down here to this node v3, and we've paid, at this point the heartbeat is we paid for creating a task. We're going to have a heartbeat. What we're going to want to promote, do is promote the task corresponding to this subtree, right? That's the outermost parallelism in this case. Okay, so let's step through it. So at this point, where we're at where we're starting at v3, our stack looks like this. We have a frame corresponding to the continuation of v4, a frame corresponding to the continuation of v5, and then at the top level continuation, which is just finishing the program. Okay, so the heartbeat happens. It causes this function try promote to be called. That's called by one of the loops. And effectively, what this promotion is going to do, first, it's a multi-step process. First, it's going to sort of pop this overall continuation frame off the parent stack and put it into a join continuation that we're creating right now. And it's going to initialize a child task, which is going to handle this v5 tree. Okay. Jogging my memory here. Okay, I think, yes, okay, so we're just continuing. We've done that, and now, now we call the fork instruction. So that's just going to, now the promotion handling is done, and it's just going to start running the child task. Okay, so the parent task and the child task are running in parallel. We've paid for the cost of creating the task, so it's well amortized. We're in good shape. Then, just like before, at some point in the future, one of these two, the parent or the child task, is going to finish first, and then at that point, our refactoring guarantees that whichever one finished first is going to call join. It's going to resolve the dependency edge, and then the same thing is going to happen later on when the child task, in this case, finishes. So that's basically what's going on. I won't linger long, but this is actually the code that implements that behavior. It's not very complicated, really. This part is finding the outermost instance of a promotable task by looking up in the stack for the outermost kind of parallel continuation. That one, in this case, the only frame in our stack that it has any parallelism associated with it is the case where we've gone into a left branch and we're serially, and we're waiting to process a right branch. That's this KS branch 0 case. KS branch 1 is the other case. So okay, so that's what this is doing. And this part is basically the same pattern we saw before. We create a child task corresponding to what we do in this promotion. We create a child task corresponding to our right branch, and we introduce. Or sorry, this is the join continuation. We create a right branch. I mean, a task corresponding to the right branch of the promotion point. We create a join task, schedule it, and before returning to the parent task, we do some surgery on the parent continuation, so that basically the behavior is that both the parent task and the child task do the appropriate join instruction to synchronize with the join task when they're finished. So basically what we've done, we've interleaved the sequential algorithm with the parallel algorithm, so that it's as if this sort of heartbeat timer thing is guiding the interleaving in a good way, and this whole logic here is just basically giving us the illusion that we had an oracle to begin with, and it just is picking the right algorithm at the right point. And so okay, so basically that's how we did it. So what does it actually give us? I mean, this is a silly program, but it's not entirely trivial to parallelize it. So these are the results I got from running on a machine with 64 cores. This is the serial iterative algorithm, right? Not terribly interesting, but okay, we have two kinds of inputs that are interesting. These ones are just nice, big, balanced trees. This one has like some random insertions to make it a little more interesting. But these are sort of the highly parallel cases. So here is the speed up we get with our refactored version. And this is the speed up you get with Silk without granularity control. So it's significant, noticeably smaller. And that's because of the overheads Silk is paying. And this is the speed up you get with Silk when you do granularity control, but so it is a little bit faster. I think the gap could be narrowed to practically 0, but actually this algorithm is kind of bogus, but yeah?
Is that another algorithm, or is it like manually?
This is, yeah, so Silk plus granularity control is just basically, I set a threshold at which to stop spawning tasks. So if you get below a certain threshold in your recursion, you just stop spawning tasks. And that sort of thing is useful for getting a reference for what if we had an oracle, if Silk had an oracle that could tell it when to stop splitting it, because I had to obtain that through like a little tuning process. You're not going to do that it actually doesn't even work in general, because it only really works well for particular tree structures. So it's sort of but anyways, what it's saying is, I would sort of conjecture, I did a very, one thing I didn't mention, one thing to making this refactoring efficient that you didn't see, is I did a silly thing in the refactoring. I actually store, the representation I use for continuations uses a linked list, but I just store it in an STL deck data structure, so I don't pay for the linkage. It's just flat. Okay, but that wasn't actually the fastest thing. This gap can be narrowed, I'm pretty sure. The other thing to notice is when you go into the low parallelism world, this one has some parallelism, but it's not a lot. It's enough to keep our cores busy. This one has practically zero parallelism. Silk will crash because of the stack overflow, and ours will get some speed up here, and it's not as fast as the sequential algorithm. That performance can be improved, but it's basically there's very, very little, or there's actually no. This is a change. There's no advantage to parallelism at all. So it's basically all downside for our parallel algorithm. So it's actually not too bad, I would argue, and can be improved. Okay, so before wrapping up, I'd just like to say thanks to all the reviewers. They had some really awesome comments and helped out a lot as I improved the draft. Okay, so So basically what we did was one of a number of applications of this sort of classic idea from going back to Reynolds and Donvey and so on, of using CPS conversion and defunctionalization as a way of transforming our programs. They sort of thought of it, maybe traditionally it's more used in compilers. What was interesting about Koppel's blog post is it got me thinking of it as a refactoring. Now, I don't know exactly what particular usefulness it has, except for as a teaching tool maybe, or solving one-off parallelization problems that are really tricky like this one. But there might be others. I haven't really explored it that much, just a few programs that I bothered to do this technique on. So there might be other interesting applications. Basically what we did, we started from a recursive kind of trivial, like recursive spec program, and got to something that was fairly sophisticated in the way it could deal with parallelism on a multi-core system. And the kind of the technique that we used at the end to do the merging of our two kind of optimized algorithms was this technique called heartbeat scheduling, which was also sort of, as long as I've been working on it, had been sort of a compiler's technique. And this is just sort of pointing out that it doesn't have to be. It could be useful potentially for one-off parallelizations, or maybe some other kind of in between, like a sort of a rewriting tool, perhaps, that rewrites C to C sources or something like that. So, yeah, I think that's basically all I had. So. Yeah.
Hey, Mike. Okay. So, crazy idea. I mean, could you imagine taking this and actually putting it into a compiler? So this was refactoring that you did by hand.
Yeah.
And to explore the technique and everything. So like, first question, can you imagine putting it in a compiler? Second question, it occurred to me like, oh, hey, we listening to Gilbert's talk earlier. Gilbert was talking about user scheduling, right?
Yeah.
And like,
yeah.
I'm like now imagining like, oh, what if I just, tell the compiler like, hey, reschedule this via heartbeat, and like it'll do it for you. I don't know. What do you think is the feasibility here?
Yeah. Well, I can only say I have hopes that because these refactoring steps are so, you can almost just say like, okay, do tail call elimination. It's just getting the sequence of things right, and they're not very terribly complex things. You could imagine thinking of it as that kind of DSL-based, approach where you have a scheduling language that tells you what refactoring steps to take in what order, and yeah, but that I think would be a very interesting, meaty research problem. Yeah.
Any further questions?
Thank you. I think this is a really surprising result that you present here, because intuitively, if I think about it, the greedy scheduling of Silk should always outperform you, because essentially, if I understand correctly, the decision that the heartbeat has passed and actually I should do it is rather late. So
it starts. It goes sequentially first, and then it only starts after it. Yeah.
So that means essentially, the other cores are idling up to the moment when you say, okay, maybe it had been a good idea if I had parallelized earlier.
Yeah.
That sounds totally counterintuitive to the idea that say, okay, I greedily snatch this thing, start computing it, and if it turns out that it was too expensive, then by the time that you take the decision, because the heartbeat is gone, most likely you're even done already.
Yes.
And I was wondering, in particular, when you showed the numbers, sorry for this one question, when you presented the numbers for the second slide, maybe we see actually a mix of two effects here. Maybe your CPS transform essentially is an optimization per se that has an impact on this gain that you have.
Well, the overflow in that case was just simply because I was heap allocating. Well, this STL DEC data structure is resizable, but it is a consequence of that. But I think though what you have pointed out is that the heartbeat approach does have this potential weakness that because it's always starting any given computation in a sequential fashion, it's always like, for example, in that tree example, it's always somewhere down in the left branch before it has any chance to to parallelize for the right branch. That's just how it works. So the way that the way that we deal with that to an extent is it's always going to it's going to reduce parallelism to some extent. There's a proof in the original paper that shows that the actual extent is in proportion to the heartbeat rate. So it's how aggressively you want to sequentialize basically is determining that. But it tends to be fairly small. So it typically shows up when you're running against the limit, like your workload is not really it's only going to show up when your workload is not really large enough to keep all the cores fed. So if you're iterating that process, you're only able to keep like half the cores fed, then it might be somewhat noticeable that it's over sequentializing. There are other approaches for dealing with that, but the other thing I would say is that we actually use a work stealing scheduler behind the scenes. Heartbeat is sort of a additional layer on top of the work stealing scheduler. So it's using like the same underlying techniques as Silk is using. Basically, like it's a slightly different implementation of work stealing, but the same kind of optimizations are working behind the scenes.
How fast was the heartbeat?
It's a very. We set it to be just to be small. The smallest possible we can get away with. So it's like 100 microseconds. In practice is what's good with like a 2 gigahertz machine. We found.
Unrelated questions, if I may. I was wondering, could you just adjust the runtime system of Silk, not to immediately steal, but only to steal based on a heartbeat? Then you wouldn't have had to have different versions of the code and do all the merging.
Yeah.
And all that.
Yeah.
That would allow us to compare the schedulings against each other, not having this potential effect of defunctionalization in investment.
Yeah, I think that I'm not sure if so there's a similar idea I have in mind that where you can kind of take this basic approach and just merge it with the load balancing algorithm. So it's like what that would mean is like instead of like promoting, you just have like your call stack is like another version of your work stealing queue. It wouldn't be concurrent in that situation. We have so that was sort of one idea potentially, but yeah, you make a great point that the existence of the deck itself is a bit redundant. Like if we could just have the stealing occur directly on the call stack, for example, and that would basically give you a different load balancing approach. So I think both versions are useful for sort of the basis for comparison against like Silk or TBB.
Thank you.
Yeah, thanks.
Last question?
Yeah, there's an online question. Right?
Okay.
So they basically ask if the code is available online.
Yes.
And you can
Let me think about how. Yeah, I'll have to provide a link because the paper is linked, but the code is not. Yeah, I don't think there's any publicly available link. I'll put it on my website. Let's say I'll just make it. If you just search for it, it'll be present. Get that done in the next day or two.